Well, hello and welcome YouTube to Mr. Robinson's Q&A Power Hour. This is for Integrated Math 2. If you want to find the supporting Integrated Math 1 video that I did for this series of Power Hour videos, you can find it in my YouTube, just my most recent uploads. This is a most recent upload, so is the Integrated Math 1. In Integrated Math 2, we are focusing on, we just did a module on simplifying exponential properties and simplifying exponential expressions and radical expressions, understanding their properties, like multiplying bases, adding exponents, different things like that. We just came off that, we quizzed that, and we are now focusing on graphing exponential functions. Graphing exponential functions, we'll get into things involving percentage, increase, decrease, things like that. We haven't looked at that yet, so we'll see what kinds of questions we cover, but any of those two things would be relevant to what we're doing in these last couple weeks. Now, what is the Q&A Power Hour stuff? Well, I'm glad you asked. You see, every 2 weeks, I ask my students to submit questions for me, for which then, when that Friday comes up, this Friday, January 22nd, 2 weeks come up there, I will record a video and answer those questions. They receive credit for asking the questions, and, they choose to decide how much it's worth for them for 10 points of credit to ask the questions here. So I only have 6 questions on here. I haven't read them yet. I just pasted them in and started the video. So we'll go ahead and see what those questions are. They are asked and answered in the order for which they are received. For the students to receive full credit on these and for it to make most sense for what they're doing, the questions should be relevant and current. So what that means is within the last couple weeks of what we learned, and they should be relevant, and they should be content related. So we just did a video that was curriculum related to start off the semester to get their feet wet on the Power Hour stuff. I have a lot of new students in this semester, so I thought that I'd help them out understand how this works, but they're not asking curriculum questions anymore. At least that's not the plan, not for full credit at least. They should be asking content related and relevant questions on these ones. Okay, I'm going to go ahead and move forward here. If you want to find a specific question once you see the deal for what these questions are, go to the description section down below. You'll see the questions down there, and you will be able to find a timestamp for that related question. All right, let's go ahead and get started with this one here. And the first question that's being asked is, what do you do if you're working in a group and nobody speaks? Well, okay, so this is curriculum. What do you do if you're working in a group and nobody speaks? Not lose your parts of points. For the homework, quizzes, and tests, are we allowed to use calculators? All right, so before I answer the question, let me state 2 things of that. Number 1, this is a curriculum. This is a curriculum. These are curriculum-related questions, number 1. So credit-wise, not going to get very much. I will answer them. Number 2, try, if you can, try and ask the questions in different, so they have a submission form. Try and resubmit the form again. Put your name in again, submit the form again to have them separate. For several reasons. One of them is I sometimes forget to answer the other question, unless it's exactly related. That's why I started reading more, because I thought you were saying, like, for the homework we can work in groups and it's something. I didn't know what you were going to say there. So if you ask that second question next time, resubmit the form, because like I said, I don't go and read these and do whatever. I don't know, it takes too long for me to do all that. So if you can do that next time, that would be appreciated. Okay, let me try and remember to answer both. First question. What do you do if you're working in a group and nobody speaks? Not lose your part of points. So to keep in mind and to kind of bring into context what this person's talking about is, if we're doing a group exam, which we haven't done any yet, so we're still trying to figure out how this will look. In actual physical class, non-COVID way, not too bad. In Edge Elastic, in Zoom, we'll see. we'll see. I don't know that answer, especially when it comes to sharing the points, because here's the thing. Everyone in that group receives the same credit. That's to hold accountability. That's to make sure that everyone's doing their part. Let's hope no one's sabotaging somebody else. Now, to answer your question in several ways, what to do? What do you do if you're working in a group and nobody speaks? Ping me. And when I say ping me, I mean that when we're in Zoom, I'm in the main room or I'm in another breakout room, and there's a part in Zoom on the bottom when you're in a breakout room where you can request, I don't know if it says ping instructor or request to ask instructor, ask a question, whatever. You can ping me and I get a display notification, room 2 needs your help. All right, something like that. And either I can go there immediately or I can't, I don't know, but ping me and I'll go to you. Tell me the situation, mic or private chat, tell me the situation. This person hasn't spoken up. Then I'll try and reach out to them. Hello, are you there? Yes. Or silence. It's silence, I'm going to boot him. If yes, okay, what's going on? Why haven't you spoken up yet? blah, 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 blah. Okay, do you understand the gravity of the situation, whatever. So if they can't come to terms and understanding with the gravity of the situation in the group exam thing, I will also boot them, not from Zoom, but I will boot them from the group exam, and they'll have to kind of do it on their own. You won't be held accountable for them. I'm hoping that doesn't come into play, because what I'm really hoping is that group exams are more for those who are struggling, and if that student is struggling, I'm hoping they're paying attention, responding, sharing their screen, asking questions, making sure they can make sense of it, because they still have to submit their own scratch work. If I'm grading their number one, I'm looking at their number one scratch work, not yours. And if they only filled in the answer to that thing, they need to put the scratch work necessary. So I'm hoping they're doing that stuff to make sure they get free points. They're learning something from you, or they're at least receiving something from you. And I know that kind of sounds like whatever, but I'm hoping they're learning something from you. I'm hoping they also get a little incentive to kind of build on the up and up. If they're not doing too well in the class, that gives them a little grade boost. That gives them incentive to keep going on. So I am hoping for that. Now, here's another scenario that I want to talk about. I also hope this doesn't happen, because I'm going to do something. I'm not going to tell you what it is yet. But I'm going to do, well, actually, I'm going to do two things. I'll tell you what one of them are. I am going to try and get some people in your group who you think you can work with, because I am going to survey you guys later and ask who are some group members you like to work with. You're not going to be able to work with all of them. I can guarantee you that. Maybe you'll get to work with one per group test, okay? And we only have like 3 or 4 group tests. So you get to work with one per group test, maybe, at most. I'll say, hey, name your top 3 in any order. And I'll see if I can arrange something like that. So at least you have a little bit of something. Because if no one's speaking, that's scary. You have a group of 4 and you're the only one, or no one's speaking to each other, that's a problem. Try and turn on your webcams. Definitely try and turn on your mics. But there's something else I am going to do that will more or less kind of enforce people to respond to each other. Okay? You don't know what it is. I won't tell you what it is. You'll see it on the first group test. But we'll see how that goes. And if they don't respond with that, yeah, let's boot them. Okay. So I hope that answers that question in full. It's a good question. I almost moved on. This is why you don't do this. Your next question was, for the homework, quizzes, and tests, are we allowed to use calculators? By and large, when you get higher up in math, using calculators is generally a conceit of what you do. As in the stuff that you're learning, like as in you already learned how to do the addition, subtraction in ways that it makes enough sense that, okay, now use the calculators. Sounds kind of weird. You know how to do it? Okay, now we'll give you the calculator. You don't know how to do it, then take away the calculator. Sounds kind of weird, but the idea is you're learning more powerful stuff now. You're learning the higher complex stuff that we don't need the calculator stuff to get in the way of you getting an answer wrong, or of you spending time on learning how to do the new stuff. So the calculator can often come into form here. That being said, when you're asking this, we're in distance learning right now, and it's hard for me as a teacher to refrain from not letting you use a calculator. What am I going to do? Go in your house and take it away from you? I can't do that. So it's hard to take that away. That's why when we were doing the most recent ones and I talked about the power table stuff, I recommended you to try and avoid using the calculator and use the power table for several reasons. A couple of them are as follows. Number one, I don't want you to have to resort to the calculator for something times when you're actually not supposed to be using it. And I don't mean in times that I don't want you to. I mean in times that you're not supposed to. If we have the square root of 8, I don't know the square root of 8 off the top of my head, it's 2 point whatever. I don't want you to approximate it 2 point whatever. I want you to either leave it as the square root of 8 or simplify that radical as 2 root 2. And, the calculator is just going to give you a decimal approximation. We got to be able to do something else with that square root of 8. Or like a fraction, like 9 over 5. Let's say 5 over 9. Calculator is going to give you 0.5 repeating, and you might round that or so. I want you to leave it as 5/9, so you might overuse the calculator, and I don't want you to. So that would be an example. There are some times where if I didn't want you to use a calculator, it's either because the test or quiz or whatever is specifically about needing you to calculate. Like, I'm testing your ability to calculate something in a certain way. I don't know what it is off the top of my head right now. Like an order of operations thing and show the work. Or it is something, like I said, where you do need to show your work, where I'm saying, like, hey, I want you to calculate this and show all your work. Carry the 4 and do that kind of calculating stuff. For the most part, you can. I do not want you to use your phone as a calculator, though. Please, I do not want you to use your phone as a calculator. That opens doors to things like websites and apps, and let's stay off of that. You should have a scientific calculator. Your computer has a calculator. If you go to the search menu and type calculator, it has that as well. Try and refrain from using phones or websites. Try and use a scientific calculator or your computer at last resort, or just ask me, Mr. Robinson, what's whatever times whatever, and I'll give it to you. Even if I have to use a calculator for it, I'll give it to you. Okay. I won't tell you if what you're doing is right or wrong. Just like a calculator doesn't tell you, hey, bonehead, while you're doing 16 times 8, you're supposed to be doing 16 plus 8. You know what I mean? So, all right. Let's move on. No. All right. That was not content-based, though. So remember, credit-wise, not much. When you have a square root inside of a square root, once you find the square root of the one on the inside, do you have to find the square root again? Okay, so I'm imagining there's a comma. When you have a square root inside of a square root, comma, once you find the square root of the one on the inside, do you have to find the square root again? Well, yeah, if you have a square root within a square root, yes. And we've seen different examples where it's not literally just square root, square root. We have a square root of something, and within that something, oh, here's another square root. And within that something, we've seen something like that. Regardless, yeah, a square root inside of a square root is not a redundant thing. In other words, they're not saying, why did they do this twice? Let's just take one away. No, square root literally means second root. And second root is also equivalent to raising something to the 1/2 power. So what happens when you take something to the 1/2 power and take that to the 1/2 power? We know that as multiplying your exponents. And what's 1/2 times 1/2? It's 1/4. So you know what the equivalent is of taking the square root of a square root? It's taking the 4th root of a value. So if I asked you, what is the square root of the, and I'm trying to do this here instead of just using the whiteboard. I might jump to the whiteboard in a second, but I'm trying to make it verbal. So if I asked you, what is the square root of the square root of 16? The way that you asked it, you can do. You can take the square root of 16, which is 4, and then the other thing, take the square root of 4, which is 2. Or you can do the other equivalent. The square root of the square root of 16, take both square roots and do whatever you need to do. Either go and raise them to powers and convert it, whatever. But eventually that can turn into the 4th root of 16. And what's the 4th root of 16? Well, what times itself, times itself, times itself is 16. You can use the power table. That answer is 2. So the 4th root of 16 is 2. And the square root of the square root of 16 is also 2. So do you do it twice? Yes. Now, like I said, there are ways that you can work around that to make it easier for yourself. If you raise them to fraction exponents and work on that math, that can also help you figure out what you want to do. Because they're not always square roots. They could be cube roots and things like that as well. So I hope that answers your question there. And that was content-based, and that was relevant in the last 2 weeks. You'll get full credit for your question. All right, the next question is, how do you calculate the residuals for lines of best fit? I'll answer it, but listen, this is not relevant to what we're doing right now. No, this is content related, but it's not relevant. We have not done statistics and scatter plots. If we ever do them in IM2, which we won't, we might have, I don't know if you do them in IM1. I don't know when you actually do these. It's scheduled, I shouldn't say scheduled. It's baked into the IM1 curriculum, but pacing-wise, we're dropping statistics because time-wise and distance learning, it's not working. How do you calculate residuals for lines of both lines of fit? Okay, I'm just gonna assume one line of fit because you do it for one, doing it for the other is the same thing. All right, I don't even know. I think sometimes people try and ask questions either to troll me or they're trying to sneak some credit in. You're not gonna get credit for this question. I'll answer it. You're not gonna get credit for asking this question. Just so you know, even though it's content related, it is not related to the math we're doing here. All right. For those who don't know what a residual is, probably even this question asker, I don't know. For those who don't know what a residual is or a line of fit, this is involving what are called scatter plots. A scatter plot is a graph or a set of a table of values where they're relating two different things, such as hours of sleep in the night and grade percentages for things. You know, they try and find a correlation of things. So, hey, you get less hours of sleep. This person got 2 hours of sleep. They got a 20% on the test. This person got more hours of sleep. They got a higher grade. Scatter plots show they relate something like hours of sleep and blah, 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 blah. So these are all different data points for different people who got a certain grade based on certain hours of sleep. And what you tend to see sometimes, I'm trying to kind of give it that form because nothing's exact. You know how we plot lines and curves through points? A scatter plot doesn't necessarily provide that same instance, and what we do sometimes is we try and draw what's called a line of best fit, or a curve of best fit depending on what it is, but this looks rather linear in nature. So in drawing a line of best fit here, this is maybe the line that best goes through these points, so we can construct a model that approximates or predicts what kinds of things will happen in the future through extrapolation, or say, what do we expect someone to get on a test if they got 6 hours of sleep, whatever. Now, the closer that the points are to the line in general, the more relative this line has to do with anything. Like, like it has a stronger correlation between hours of sleep and grade percentage. So, if there were other points that were like this, hey, we got a lot of hours of sleep but low grade percentage, and we got no hours of sleep, we got high grade percentage, this line of best fit this isn't really a good model for anything more, because there's no real correlation between the two. But the more that you see them like this, and I'll only erase just a couple points here, the more that you see a tighter focus on that, if I take away some of these points here, there seems to be a strong correlation between you get more hours of sleep and you get a higher test grade. Now, I'm over speaking on this, I know, but this stuff's interesting, so I'm just going to talk about it here. That doesn't necessarily mean that more hours of sleep causes a higher test grade. Recall that there are, so this is something called correlation. Correlation doesn't always mean causation, meaning getting more hours of sleep doesn't necessarily mean you'll guarantee yourself the better grade. More hours of sleep could also be a lurking variable for somebody who has less stress in the night. And if you have less stress, maybe you're better focused for your test, or you better prepared yourself. And and on the converse of this, maybe less hours of sleep means that you studied longer, so that could be a reason why you've got a better grade. But in this case here, it's things like that. Or maybe more hours of sleep means that you maybe you're not doing other extracurriculars during the day, so all your focus is on the studying, so you get those hours of sleep, and therefore all your focus gets to attend yourself. So there are other things that could cause it, and it's not the sleep that caused it, and you're like, oh great, I'll not study and I'll just sleep and I'll get a better grade. That's not necessarily what it means, but there's a correlation, and you can find other links with it. Now, they're asking about residuals, and a residual would be an entirely different graph if you graphed it, but what did you say, how do you calculate them? A residual basically just means what is the value error from an actual data point and your line of best fit. So let's say here that this was a person who slept for 2 hours and got 20% on their test. Yet in my line of best fit, what we kind of predict, because we just drew a line of the best fit through the points, our predictive measure says that if you get 2 hours of sleep, we predict those people will, more often than not, get about, let's say, 25% on their test. Okay. A residual takes what someone actually got on their test, and you subtract it from what you predict someone to get on their test. So the residual for this data point here, for the person who got 2 hours of sleep, that residual is minus 5%, meaning somebody actually got 5% below what was expected. And this residual could be someone that got 7% above what was expected. So residual is the error, which there will be error unless you have exactly going right on a line. That's just not realistic in any scenario for any model for anything that you're trying to gather data on, real life data on. But this residual is 7% and this one is 2%. So negative ones are when what's expected is below your line of best fit. So maybe negative 10%, things like that. And then positive residuals are what's above. And a 0% residual means that you're right on the line. Okay, so that's what residuals are. So how do you calculate them? You subtract. You determine your line of best fit. You find out what the equation is for it. Calculators can actually give lines. And here's the thing. What calculators do to actually determine a line of best fit is they actually do something involving the residuals. So they figure out what minimizes your residual amount to give you a line of best fit. And then you can calculate residuals off that. So calculator kind of does a self-referential thing like that. But if you have your line of best fit and you know how your model is doing whatever, to say when I plug in this value for X, I get 25% for Y, then you subtract your data point-ish stuff from there. So this is neat and this is interesting. Unfortunately, we're not doing statistics right now. So I love the question in that way, but not relevant. So anyway, it's a subtraction. What is the actual? So residual equals actual minus expected. What did somebody actually get? Take it away from what the predictive line would tell you. It's just, I mean, you're not going to get credit for this question. I don't mind answering it. It's the power hour. I don't mind sticking around doing it, but I hope you learned something. I hope people watch. I hope you guys learned something here. So there you go. Residuals. Statistics are great. They are my favorite. They're hard. They can be hard all depending, but they seem to be the most relevant form of math when it comes to real world problems. Things that we can actually do something with. Data collecting. I'm a softball coach, so statistics and stuff, residuals, this stuff matters to me. I'm actually doing something right now. I'm not going to get into it, but it has to do with topspin versus backspin and predicting certain exit velocities and launch angles, how far you'd actually hit a ball with a certain amount of topspin and backspin, or how a player would do it given what they've done. And all that stuff matters. Lines of best fit, residuals, all that stuff. It all matters. All right, here we go. What is an asymptote and how does it relate to graphing the exponential functions? Okay, yeah, so we just started learning asymptotes here on, I think, Thursday, so yesterday, so on the 21st. An asymptote, it's a feature on a graph, okay? Just like, like in a circle, you know how sometimes people draw a center on a circle? The center is not actually part of the circle. It's a feature of your circle. All the points on the circle are the circle. The center is just a center. So an asymptote, it's not actually a part of the points on the graph, but it's a feature that helps describe what your points are going to do on a graph. And here's the thing about exponential functions. You can't raise some base, some non-zero base, because we don't use zero as a base. We can't raise some base to an exponent and get 0. Because what we do is starting from 1, remember the definition of exponentiation, is we ask how many times are we multiplying by that number. Well, starting from 1, you can't multiply by any number any certain number of times and get 0. Unless you're talking about 0, but like I said, we're not using base 0. So it's impossible to get 0 from raising a base to a certain exponent. Okay, so what I'm saying there is, here, I'll kind of give you the math equivalent there. So if I had any x to the y cannot equal 0, assuming that x itself is not 0, right? Because 0 to any non-zero power is 0. Okay, so I hope that makes sense. Now, what does the asymptote have to do with? Well, an exponential function talks about how many times you multiply by something over and over, and oftentimes you experience exponential growth when you're doing that. So something takes off in one direction. But then you also are dividing by something over and over. Excuse me. You're dividing by something over and over in the other way, and then it's shrinking, right? And shrinking. Well, let's just take this, for example. Let's say I had some number. Doesn't matter what it is. Just imagine you had a number, and we divide it by 2. You take half of it. Take half the number. All right, let's take half the number again. What do you got? Take half the number again. What do you got? Take half of it again. Half of it again. Take half of it 1,000 times. Is that number really small? Probably. Is it 0? No. Might as well? Should it might as well be 0? Maybe. But it's not actually 0. Actual true 0 cannot occur just by taking half of something over and over. So the asymptote is that dotted line that we're seeing on our x-axis that's saying our graph's not going to cross or touch this dotted line. It helps describe that feature, and you might not think that it matters that much when your asymptote's on the x-axis to do that, and I'd partially agree with you, because if we have the x-axis line there, why do we need a dotted line on top of it to help describe what we already can see in front of us? Well, the answer is because asymptotes aren't always on the x-axis. So, although, and here's the other reason, because I don't want you to cross it. So if we have a graph that's doing an exponential function that's doing something like this, it converges toward it, it gets closer and closer, but it never actually truly touches, right? But here's the thing, and we're not doing it together for us, but there are exponential functions with vertical shifts. Meaning, instead of the graph being right here, what if it was up here? Well, guess what? Or let's say down here, because I don't use the arrow. Guess what? Its horizontal asymptote goes right along with it. The asymptote states that I can never cross -2. I can never touch across -2. Right, there's that. Now, these are horizontal asymptotes for exponential functions. That's how they relate. So I answered how they relate. The whole, if I take half of something over and over, I'll never actually truly reach 0. You know what I mean? So that's an instance of that. And that's what all exponential functions do. They take off on one side, they converge on the other side, and this feature kind of helps level off for you and say, we're never gonna touch across this value. It just won't happen, ever, period. No matter how far you go, it approaches it. And that's what we talk about with end behavior. Now, the asymptote is a dotted line that kind of helps describe that feature. And why is it important? Because not all our asymptotes are on the x-axis. For what we do, I guess they will be. You're going to be learning some other things, though, down the line. In IM3, you will be learning about rational functions. And with rational functions, you'll be dealing with vertical and horizontal asymptotes that might be something like this. Here's a vertical and horizontal asymptote. And believe it or not, there are graphs that do something like this. They are not hard to calculate and make sense of and use. There are graphs that do something like this. They just never touch those points and never cross them, and they do something that weird looking. This is an example of a rational function that has vertical and horizontal asymptotes. You may be, I assume in pre-calc, you'll be dealing with rational functions that deal with slant asymptotes. So as we had that vertical one, you'll also possibly have a slant asymptote, and it does the same kind of thing right here. And it approaches them, and it just kind of shows, it's a feature that's kind of saying it doesn't cross. Graphing calculators won't show the asymptote, so to speak. You'd have to just write the equation of the line that does it, but the graph will naturally just not cross those because of the behavior of the function. So you'll deal with slant asymptotes. And when you do trig functions in pre-calc, periodic trig functions, and you do things like tangents, so you don't have to know any of this stuff now, you'll be doing periods of vertical asymptotes over and over and over again, and you'll see these graphs that come in waves. They approach this thing, and they go to the other one, and they approach on that side. Sorry for making a squirrely drawing here. And it does it again and again. This is why it's called a periodic function. It does it again and again. These all have relevance. These all have meaning. These all take form in a certain way. You notice I do the half arrows when we approach asymptotes right there as well. I'd like to see you try and do that. You don't have to. But that's what asymptotes are. They are just boundary lines saying you shall not pass. There are exceptions to asymptotes that are passed at times, but that's if they're in the middle of a function and not regarding end behavior. I'm not going to show those. Those have to do with rational functions. They're very complex looking. So every so often you might see something that crosses in the middle of a slant or horizontal asymptote, but the end behavior ones won't cross. And those are the ones we're referring to, end behavior for exponential functions. Do I want to answer anything else for your question there for asymptotes? I think that's it for now. For our intents and purposes, guys, our horizontal asymptotes for all exponential functions have horizontal asymptotes, and non-shifting exponential functions will always have a horizontal asymptote on the x-axis, which is what we're dealing with here. Let me say one more thing to this thing. Let's talk about in terms of like a decay thing. I don't know if you guys know this, but when you take a medication, when you take medication, they all have what's called a half-life, which just describes how long it takes for that medication to have half the amount of substance as it previously had in your body. So you take half an amount, half an amount, half an amount, and over, you start to get less of that medication's active ingredients or whatever in your body. So as it decays over time, it gets closer and closer to you losing that amount in your body. You know, when you drug test, stuff like that, whatever, they still find trace amounts of it. There are some that are so insignificant that you can ignore them. I don't know what threshold that is, but there's never truly zero amounts of it in your body unless you have a way of like dumping it out. So, you know, I took Benadryl a week or two ago, you know, whatever. There are still, even though I feel no ill effects of it, even though a thing might not report high doses of it, there are still trace amounts of it in my system. And it's just saying I will never really get rid of that stuff unless it filters out a certain way in your blood and you like lose the blood or whatever. I will never actually lose trace amounts of that in my body. So either 0.000000001% of it in there, but it's still there. It's still there. Kind of weird to say, but it is. All right, so that's it. That was a lot that I answered there. Sorry. Hopefully you'll get a lot of points for that because as much as I covered with the examples. All right, next question is, are there any tableless graphing methods for exponential functions? I'm glad you asked. The answer is yes, there is. We haven't covered it yet. I want to cover it on Monday. Now, I'll cover a really short thing of it with you. Actually, you know what? I'm not going to get deep into it here. What I want to state is that yes, there are, and we'll do it Monday, because you didn't ask how do you do it tablelessly, because you didn't know whether or not the answer was there. What I do want to state, though, is there is a nifty concept to the, you know, when we did quadratic functions and we had this right here with h and k, and you know how h and k was the shift of your vertex, or at least it was a shift of your points, and absolute value functions were the same way here. There's that vertex form of this. Not that exponential functions have a vertex, but they do have a base starting point that you can consider, such as the y-intercept. And we're not doing shifts, so what I'm stating does not have to do with us in full. But there is relevance to even exponential functions that appear and occur like this. This is the general form of an exponential function, and h and k both also represent horizontal and vertical shifts in the same way that the others do. Notice how they say x minus h, and we do that whole opposite same thing. This has an opposite same effect. That's one portion of it where you don't have to plug in a value for x and compute all this stuff, where you can do that. And yes, a and b have very specific relevance that I will get into with you guys without shifts. Without shifts, there is significance to a and b which we can use completely without a table that I am very, very happy to show you starting Monday. Okay? So, yes, A will have to do with something. I think you know what A has to do with. I'll tell you that. A, for now, with no shifts, A is your y-intercept. With no shifts, A is your y-intercept. B is what's going to be called a growth factor. And in exponential functions, as we understand, this is just your little teaser, as every time x increases by 1, you are multiplying another amount of your base value over and over, right? What's the difference between 2 to the 5th, which is 2 times 2 times 2 times 2 times 2? I said one too many 2s. And 2 to the 6th, 2 times 2 times 2 times 2. Oh, I have one too few fingers. What's the difference between 2 to the 4th, 2 times 2 times 2 times 2, and 2 to the 5th, 2 times 2 times 2 times 2 times 2? The difference is this one has one more power of 2. Yeah, I multiplied by 2 one more time here than I did here. So what do you do going from something where you're plugging in 4 for x and 5 for x and your base is 2? You multiply by 2 again. You multiply by 2 again. So going forward, multiply by 2. Going backward, we would divide by 2. So I'm giving you the hints of it. I just don't want to do the full thing. I want to give you the verbal description. See if you can use that teaser jumping into Monday. That would be a nice approach for you. Very good question, though. You'll get full credit for it, of course. Because that is piquing the interest of, I'm interested in this. I know the table stuff can take some time. You've talked about tableless graphing before. And by the way, these are not the only ones that do tableless graphing, guys. I just mentioned rational functions. You might not know what they are yet. Rational functions do them. A over x minus h plus k. Cubic functions, you can cubic. Quartic functions, you can raise to the 4th power, like those. Those also occur. Radical functions. Whoops. Y equals a times the square root of x minus h plus k. Logarithmic functions. Y equals a times log base b of x minus h plus k. These all, using these things, all have that same kind of concept. A is a vertical stretch factor. H is a horizontal translation. K is a vertical translation. If there's an extra b, there's another portion going on in the behavior of the function, like this has a growth factor here. There was one more I had it in my head. There's one more I was going to point out. Oh, trig functions. You can do trig functions. A times sine of x minus h plus k. There's something else in sine that uses a b. I'm going to ignore that for now. Yeah, so all of these do that same thing, and there's a tableless form of all of these. What I want you guys to remember, I didn't finish answering this question. Here we go. What I want you to remember is this. When we graph, we are, in large part, in some way or another, approximating some of our solution, some of our points. You guys know that when we are plotting points and connect the dots, that connecting the dots is getting other points for us, but those are approximated, because unless we have a perfect scientific measure like with a ruler, our curves are always approximated getting those points. So we're only getting the critical points that we can see fit. Tableless graphing is a way of understanding the behavior of your function and doing that same thing. I could do, knowing enough calculus, I could do tableless graphing for something like, well, you know what? I'm going to stop there because it doesn't have to do with exponential functions anymore. But yeah, in exponential functions, we get only the points that we find relevant to us and we connect the dots and we're good. The asymptote takes care of the rest. The end behavior takes care of the rest, blah, blah, blah. All right, and I think this is our final question here. I think there were only 6 questions in total. What is the difference, what's the difference between, I assume, negative exponential decay versus negative exponential growth? Let's just talk about growth and decay in general. And then, well, you know what? The negative one is really important for what you're asking here. So, okay. Let's just talk about growth versus decay to start with. Growth has to do with increasing the amount of content of whatever you're doing in the direction that you're going. So to us, in exponential terms, that means separating from the asymptote. If our asymptote's on the x-axis, exponential growth means as time goes on, we're separating from the asymptote, whether it's positive or negative. Growth does not mean going up unless you are referring to the direction. It's going up negatively means it's going down. So exponential growth means it's separating itself from the asymptote because our growth factor is greater than 1, we are multiplying by that amount. Now in real world context, think of this like, here's a good example, think of this like a car that's driving, and x is time and y is some sort of distance measurement here. And if your car is doing something like this, remember, it doesn't mean you're driving uphill, it just means you're separating distance from somewhere. It means you're speeding up over time. See, if it's linear, it means you're going at a constant rate somehow. But this means I'm speeding up over time, I'm accelerating, I'm exponentially growing my speed, my distance, I should say. Pretend like that's a car driving forward, though. What would negative mean for a car? That might mean a car driving backwards. So it's me going in reverse, and I'm speeding up in reverse. That is negative exponential growth, that over time, I'm speeding up, but in the reverse direction. See, direction matters when we talk about growth there. So that's all about growth. Relative to direction, are you distancing yourself from what you're doing, specifically from the asymptote? Decay, positive exponential decay is starting from above the asymptote, converging toward the asymptote there, converging and getting down. Decay doesn't necessarily mean going down, but it means decreasing your elements from the direction to which you're referring. Positive would mean going down, but negative exponential decay is going up. But we don't want to say going up. We're decreasing our bits there and getting closer and closer to the asymptote. We're losing negative value. We're losing negative value. We had more negative value. Now we have less of it. Right? It's getting closer to 0, if you will. Think of this again like a car. If you're going very fast, so we're growing, we're speeding up. Now we hit the brakes. And we stop. I'm slowing down. I've decayed. It's kind of a weird word. I've decelerated. But I've hit the brakes from the positive direction. I was driving fast. I'm growing. You don't need that. But from a fast distance, brake. I've decelerated. I've decayed. I don't want to say decay, but that's positive exponential decay. Negative exponential decay in car terms, remember when I said you're driving backwards really fast? That's negative exponential growth. My negative speed, my reverse speed is slowing down, and I'm getting closer to 0 miles per hour from the negative reverse direction. So that would be an example of negative exponential decay. So what's the difference between negative exponential decay and negative exponential growth? I don't want you to think of growth as going up and decay as going down. I want you to think of growth as separation. And this is, guys, this is assuming we're going to the right. This is assuming as time goes on. Positive negative exponential growth is the separation from the asymptote as we increase in the direction that we're in. Positive direction, go in the positive direction. Negative, below the asymptote, going in the negative direction. Positive exponential decay is converging toward the asymptote as we go to the right there and getting closer to it, and we're losing bits from the direction we were in. From the positive location, we're going in the negative direction as we converge and decrease. From the negative location, we are going a little more positively, closer to 0, and going that way. So, yeah, I hope that explained it there. All right, I spent a long time on this video, guys. I hope that this answered everything for you. Check these in the description section here. Thank you for watching Mr. Robinson's Q&A Power Hour. Take care.